So let me start with a story. So the story really is what qualifies as a big number. So when I was young, your age, I worked on computers that had addresses that were either 16 or 18 or 20 bits big. And that was considered a lot of memory. So this is somewhere between 65,000 words of memory or bytes of memory and maybe 1 million words or bytes of memory. And it was considered a lot because I can remember very proudly the day in which 1 million words of memory for the PDP-6 arrived, or maybe it was the PDP-10, on the 9th floor of Tech Square. It was called a Moby, because that was, it was like 2 big racks full of memory, and it cost $1 million, and it was clearly, sort of all the memory one could ever need. But as memory prices drop, so this was considered, this is, we're cooking with gas here, guys. This is a lot of memory, and we were able to run, incredibly big programs. So the years passed, and the prices of memory dropped, and what counted as a big program started to change dramatically in terms of a data set that we wanted to process. We were doing integrated circuit designs, and simply the number of transistors. If we had one word or a little record representing each transistor on a chip, we clearly couldn't really represent it in a machine that only had a 20-bit address space. So we were very happy when machines with a 32-bit address space came along. And my goodness, that's 65,000 times the address space we had only moments ago. And the thing about 32 was it was clearly big enough for all time. I mean, it was 4 billion. I mean, it cost $1 million for one of these. So 4 billion, that just seemed at the time, okay, now that will be the architecture I'll use for the rest of my life, and happily so. Now, of course, your cell phone has 4 times the amount of memory. You got 16 gigabytes in your cell phone, much less 4 gigabytes. This can address 4 gigabytes. And so now, we fast forward, about 3 decades, and now, sure enough, we have a new computer architecture, which is 64 bits. And I'm experiencing a sense of real deja vu here, because now people are saying, clearly, that's enough for all time. Right? For sure this time. This, of course, is 4 billion times bigger than this. Right? It's another 32 bits of address space. And, we'll never have to change again. Right? So I hope you sort of sense what's going on here, is that every 30 years or so, somebody stands up and what seemed to be an impossibly large, isn't this enough to address every atom in the universe sort of things? Not quite, but, do we need to address every atom in the universe? What we're discovering is that there's a sort of trend over time that there's these sea changes in architectures where we suddenly need more address space. And in fact, maybe someday we'll get smart enough and stop picking fixed numbers for addresses and to go to some more flexible address scheme that can be, in a sense, expand infinitely large. Can you think of an address scheme that you probably use every day that conceptually can address an infinite amount of information? When you type in a web URL, right? I mean, that's an address which you can sort of make as big as you need. You can always add more characters to it to get to, provide more detail and stuff like that. So maybe computer architectures will make that transition someday. But meanwhile, at least in this course, we're talking about picking a fixed amount of computer address. And as this slide points out here, the real death of a machine comes when you suddenly realize that you haven't made the registers wide enough to accommodate more memory for the program to address. And so you pretty much have to throw away the existing architecture and come up with a new one. Now, it could be a very simple transformation. I'll just go make all my registers and data paths. I'll change all my 32s in my beta design to 64s. But inevitably, there's some challenges that come up when you add, 4 billion times as much addresses. And some of those challenges we'll look at today. But you tend to have to rethink the computer architecture from ground up. Okay, so 3 decades from now, one of you might be standing down here in front of the class and, reliving this story. Of course, you'll have to leave more room on the board as you carefully explain why 128 is absolutely the largest number of address bits one will ever need. Okay, why do we want so much address space? Well, one thing we want to do is to make sure that we keep an abstraction between sort of the addresses our program use and the actual amount of memory plugged into any particular machine. So some of you have 4 gigabyte laptops, 16 gigabyte cell phones, 8 gigabyte, desktop computers. And typically you want to run your program on all of those. So at some level, you would like to come up with a scheme for writing your program and it should just sort of happily generate addresses wherever it's running. And we need to have the hardware accommodate the type of addresses that are being generated by your program, and if you will, adapt the addresses the CPU is generating into the appropriate physical addresses for whatever machine that you happen to be running on. So right at the outset, what we're going to do is sort of come up with this notion that we're actually thinking about maybe 2 addresses. One is a CPU address. I'll come up with a fancier word for that in a second. Okay, which is the address your program generates. And over here is a physical address, which is the address that you actually send to the DRAM chips, SIMs that you bought. And the idea is that there doesn't necessarily have to be a strong coupling. Somewhere in here we may do some sort of transformation between the CPU address and the physical address. Your program, when it runs, often it needs to grow the amount of memory that it's using. So typically, when we start a program, we don't give it access to the entire address space all at once, particularly a 64-bit program. I mean, that would suddenly require more memory than lives on the eastern seaboard. And so we don't really want to say, okay, any of those addresses, ask and I'll give you an answer. So what we do is typically make only a certain number of the addresses you can ask for valid at the start, but then you can ask to increase the range of valid addresses. So there's a whole bunch of addresses, particularly in a 64-bit machine, which your program could generate, which you'll get basically a memory address error because you haven't asked for them to be accessible. Okay, so what we want to do is to have some way of having a very large address space, but sort of grow into it over time. And then finally, we're going to use regions of our address space sort of sloppily. And here's a great picture that sort of shows you how we might use regions of an address space. Typically, there's a certain sort of a fixed size set of region of a program, a running program, which represents the code. I mean, the Chrome or whatever it is you're running. The arrays, the static arrays that Chrome needs, the variables that the compiler has put off in main memory, wherever it is. And then this part you can sort of know at compile time the size of this region of memory. And some of it may, in fact, be read-only. So most of the programs you run use, for instance, the C runtime library. And in those cases, there's no reason to have 15 copies of the C runtime library for each of the programs, for the emailer and for the browser and for all the different things that you're running. And so, in fact, you make the code read-only and you figure out a way to share one copy of that code amongst all the users. So you don't waste physical address space by keeping redundant copies of things that are read-only. Then there's a stack region, which, as we know, grows as we do nested procedure calls. And we use that to store the activation records of the currently running program. And finally, there's the heap. So whenever you allocate a data object in an object-oriented language, or you call malloc in C, or you say new in Java, or whatever it is, you basically go off and you say, give me a new little chunk of memory, please, and the heap can grow. So we have these 2 regions that can grow. So typically we put this at one end of the address space, the heap, and the stack at the other end of the address space on top of the statically allocated addresses. And then we let them, and the middle is no man's land. In other words, if you ask for address here, if you haven't arranged with the operating system, it'll punch you in the nose and say, I'm sorry, your program made an illegal memory reference. But you can ask to grow the stack, or you can ask to grow the heap. and they start using addresses in the middle. So it's convenient to have a big space to grow into for big programs, but meanwhile it may be for small programs we simply don't worry about the addresses in the middle. We don't make them accessible to the program, so they don't take up much in the way of physical memory. Okay, so we really can't bound any of the usage, and in fact for most programs there's a huge portion of even a 32-bit address space that we tend not to use. So we'd like to have a scheme for dealing with addresses and their mapping to actual locations in memory that can accommodate the sparsity. And in fact, at any given time, because of this locality thing, we may not in fact be using, for example, all the pieces of code. They may only come into play when you click the special button on your browser and they suddenly says, oh my god, I got to bring in the MD5 sum generator. And so rather than loading that right off, I'll load it later when you actually start using it. So we're going to expand the memory hierarchy. This is the picture we saw the other day. We have a fast cache whose cycle time is commensurate with the needs of a gigahertz CPU. And then we have the big dynamic RAM that's storing most of the information in your program, at least the parts of the physical address space that you're currently using. And that was slower, right? Here I'm talking a factor of 3 to 20 times slower, and the cache is here to hide the long latency of the DRAM. But the DRAM is nice because it's low cost. So we're trying to get some reasonable cost system that pretends that it's mostly fast, and we saw we could be reasonably successful at that if we design say an 8-way set associative cache to deal, and maybe even a little hierarchy of caches, level 1, level 2, level 3, to sort of deal with hiding the latency of the slow dynamic RAM. Today we're going to add another level, the disk, which, as you can see, is somewhat slower, 10 to the 4th to 10 to the 5th times slower. Okay, so now you can sort of see that you can say, well, the disk can hold everything I need. On the other hand, I really don't want to be accessing disk much, because all of a sudden I take a penalty of 10,000 times going out to disk, right? It takes a long time for this mechanical platter to spin around and for us to move this head in and out. It's very, that takes on the order of milliseconds, and I'm executing instructions on the order of, nanoseconds, or, even hundreds of picoseconds these days. And so this idea of going to disk is nice from a capacity and non-volatile storage. Does everybody know what I mean by non-volatile? Does that mean it doesn't burn, Chris? No, so non-volatile just means storage that will remember its values even when I unplug the machine. Right, so typically it involves some sort of little magnetic medium where you actually are fooling with the little magnetic domains on the magnetic material, and those little magnets will stay polarized correctly even after you unplug your machine. Okay.